The next sorting algorithm we're going to examine is called selection sort. And I'm going to describe the idea, show you an implementation, and then we'll actually look at what the complexity of it is. The idea in selection sort is pretty straightforward. On the first step, I'm going to find the smallest element, which means I'm going to have to look at everything, but I'm going to find the smallest element, and I'm going to swap it with the element at index 0. I'm going to put the smallest element at the first spot. On each subsequent step, I'm going to look at the remaining list, find its smallest element, and put it at the next spot. So in the next step, it would find the next smallest element, put it at location 1, and keep doing that. What I'm going to do is constantly keep the left portion of the list sorted. And so at the ith step, the first I elements in the list are already sorted. All other elements are bigger, and I'm not going to worry about the bubbling of trying to put them into order. I could be a little more efficient about doing some swaps if I wanted, but basically the idea is to select the next element and put it in the right location. Let's think about what this might look like. And to do that, I'm going to show you a little video of Professor Guttag with a set of students actually doing selection sort. And once we've seen that video, we can come back and do the analysis of the algorithm.
All right, so now we're going to do selection sort. The idea here is at each step, we're going to select the shortest person and put them next in line of the sorted group. So we'll bring the leftmost person forward, and we will compare her to everybody else. So one at a time, step forward. You're still the winner. You go back. Please step forward. Oh, you're definitely the winner. Next. Still the winner. Next. Ah, a new winner. All right. So you can take her place. Now we'll compare. Same old winner. Same winner. No change. It's getting kind of boring. Don't fall. Same winner. Please. Oh. Close, but I think you're still shorter. All right, next. No change, which means you are the first in line. Congratulations. All right, now you step forward, and we'll compare you. You are the winner. Take your place in line. Next. It's you. And once again, we have a lovely group of students sorted in height order.
So now, let's think about what a simulation of that might look like. We saw with bubble sort, we were finding the largest elements and putting them at the end, and there was a lot of percolation of elements going through here. With selection sort, we're simply finding the next element and putting it in the right spot. So you'll notice this portion of the list doesn't change very much, and I'm now building up the list in this direction, opposite of what I did before, but otherwise it's fine. Nice, elegant algorithm. Let's build it. Before I do that, I can basically say, how do I make sure it's going to do the right thing? Simulation suggests it does, but I can use an idea we introduced earlier to say, is there a loop invariant? Is there a property that will hold true at each stage of this algorithm? And can I use that to actually deduce that my algorithm is going to do the right thing? And here it's pretty straightforward. Given a prefix of the list, that is the list from 0 up to I, and a suffix of the list, everything from I plus 1 up to the remainder of the list, then the invariant I have is that the prefix is sorted and there's no element in the prefix that's larger than the smallest element in the suffix. From the way I've described the algorithm, that's clearly going to be true. But how do I now prove it with that induction property I've used before? In the base case, the prefix is empty, and the suffix is the whole list, so it's obviously true. The prefix is sorted, and there's nothing in the prefix that's bigger than anything or the smallest thing in the suffix. On the induction step, I'm simply moving the smallest element from the suffix to the end of the prefix. Because I'm putting at the end, after that step, the prefix is still sorted. And by the way I did it, I also know that the invariant is true because not only is it sorted, but when I'm done, there's nothing in the suffix that's smaller than something in the prefix. And when I exit, the prefix is the entire list, the suffix is empty, and so I have a sorted list. So the algorithm will work. So where's the algorithm? Well, it's actually a pretty crisp set of code to write. I'm going to set up something called the suffix store, if you like, to be initially 0. And as long as I don't get to the length of the list, I'm just going to run through the loop. And what does the loop do? It says ranging from that point to the end of the list. So it's from the end of the things that are already sorted to the end of the list. I'm simply going to compare. And if the thing I'm looking at that point is less than the thing I'm looking at the end of my suffix, I'm just going to do a little swap. Now, this is a little more work than I did before. I'm actually going to do a little bit of bubbling here, but not the complete level of bubbling I did before. I could have literally just said, find the smallest element and move it. Here I'm going to reorder things to save me a little bit of time. But what I know is when I'm done with that, the smallest element in the suffix is now at the point I wanted to look at, right at that point there, and I increase my index by 1 and move on. Notice what I'm doing here. I'm taking advantage of that idea that I don't want to copy the list. I simply want to find the right pointer and then insert in the right spot. So there's selection sort. And I could try a version of that. Again, what I'm going to do is do it where I actually print out what I'm doing as I go along. And so with a variant of that, with selection sort, again on a test, you can see in this case, I see the smallest element always being placed at the beginning of the list. In some cases, I get lucky and it was already there. But in each case, I'm going to keep doing that work until I, in fact, get out a sorted list. You may notice on my computer, it doesn't print out the overall version because I am only printing as I enter it. And if I actually look at test, you'll see that, in fact, it is now fully sorted. Real question is, what's the complexity here? Well, what do I know? I'm going to have to run through that while loop, order length of L times, because I have to go through the loop to make sure that I get the next element in the right spot. Inside of there, when I do that loop, I only have to look at a portion of the list. That's basically length of L minus whatever my index is pointing to. But that still, in general, is order length of L. It gets smaller in each step, but it's still what we would call length of L. And so you therefore see this is quadratic. And it shouldn't surprise you because I've got a loop, and inside of that I have a nested loop. And that is a characteristic of that property of being quadratic, and so it is quadratic in the length of the list. But it's another way of doing this sort, perhaps timing-wise a little more efficient than the bubble sort version we saw earlier.